So far, the differential equations we've looked at involve one function and its derivatives. But sometimes we have several different differential equations in several functions and their derivatives. So we use an nth order differential equation when we want to find the formula for one function and what we can observe is the relationship between that function let's say y and its derivatives. Say y prime, y double prime up to, say, nth derivative. If this is an nth order differential equation, then we can see up to the nth derivative. So we use this information, whatever this relationship is, to solve for a formula, y equals, say, f of t. But sometimes we want to find formulas for several functions. Let's say x1 of t, x2 of t, up to xn of t. And what we can observe is how the first derivatives of these functions x1 prime of t up to xn prime of t are related to the functions themselves. And this relationship often appears in n differential equations, n simultaneous differential equations. Called a system of differential equations. So we use the information in the system to solve for the unknown formulas. Something like x1 equals f1 of t, x2 equals f2 of t, etc. xn equals fn of t. Let's look at an example of a system of differential equations. For example, let's let x1 and x2 be functions of t which satisfy x1 prime equals x1 plus 2x2, and x2 prime equals 2x1 minus 2x2. So this is a linear system of differential equations. Linear because what we have is linear combinations of the functions. Multiple of one function plus multiple of another function. So from it we can see how x1 prime is related to x1 of t and x2 of t, and how x2 prime is related to them. We can also write this as x1 prime, x2 prime as a vector equals 1, 2, 2, negative 2, x1, x2 as a vector. It's the same equation, just written in vector matrix notation. Now, a related example is x1 prime, x2 prime equals, let's say, the same matrix x1, x2 plus cosine of t sine t. So sometimes there's an extra vector of functions over there on the right. So this extra vector of functions on the right makes the system a what we call non-homogeneous system. I could just say it makes the system non-homogeneous. Otherwise, like in the previous example where there's no plus other functions on the right, otherwise the system is called homogeneous. So this extra vector on the right functions sort of like the right-hand side of a single differential equation. If it's 0, we say homogeneous. If it's not 0, we say non-homogeneous. The solution to a system is a vector of functions something like x1 dot 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 xn equals f1 of t dot 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 fn of t. So one function for each, well, one formula for each function. x1 equals f1 of t, x2 equals f2 of t, etc. down to xn equals fn of t. Soon we're going to find out how to solve a system to get the solution, but for now let's just look at some solutions and verify that they're solutions. Soon we'll learn how to find solutions. For now, let's just look at solutions and verify that they are solution. So for example, let's keep this system here. Let's verify that x1, x2 equals e to the negative 3t and negative 2 e to the negative 3t is a solution. Solution of this homogeneous differential equation. So it's a solution if its derivative vector equals this matrix times the vector of original functions. So on the left-hand side, the derivatives we have, so x1 prime, x2 prime equals derivative of e to the negative 3t is negative 3 e to the negative 3t. Derivative of negative 2 times that is 6e to the negative 3t. Then on the right-hand side, we have 1, 2, 2, negative 2 times e to the negative 3t, negative 2e to the negative 3t, which is e to the negative 3t minus 4 e to the negative 3t. So one of them minus 4 of them is minus 3e to negative 3t. And then 2e to the negative 3t plus 4e to the negative 3t gives us a total of 6. So what we got on the left-hand side and what we got on the right-hand side were the same. Therefore, this equality is satisfied. Therefore, this is indeed a solution of the differential equation H. That's good. Now let's verify that e to the 2t, 1/2 e to the 2t is another solution. So on the left-hand side, we have, let's see, derivatives of these. We have 2e to the 2t and 1e to the 2t. Now on the right-hand side we have, let's see, this matrix 1, 2, 2, negative 2 times these functions e to the 2t, 1/2 e to the 2t equals e to the 2t plus 1 e to the 2t is 2 e to the 2t, and e to the 2t minus, 2 e to the 2t minus 1 e to the 2t, 2 minus 1 is 1, e to the 2t. So those are equal, and yes, we have another solution. the general form of a linear first order because we're just looking at first derivatives and no higher derivatives. System of differential equations is x1 prime, x2 prime, etc. down to xn prime equals this matrix A11 of t, A12 of t, up to A1n of t, A21 of t, A22 of t. So we have all these n squared possible functions here. A2n of t. And finally an1 of t, an2 of t, up to ann of t. All of that times x1, x2 down to xn, plus b1 of t, b2 of t, down to bn of t. So this extra optional vector of functions there. Or to make this shorter, I guess I could say x prime equals a of t x plus b of t. So a of t is this matrix of coefficient functions. X is the vector of functions that we want to solve for. X prime is a vector of its derivatives. B of t is this vector of optional functions there. Again, we call this homogeneous if b of t is just the zero vector. So no functions are there on the right. Now, while it's possible to have functions of t in the matrix, often we just have constants. In fact, we're going to concentrate mostly on the case where there's just constants. So we'll mostly concentrate on the case that a of t is just a matrix of constants. And for now, let's concentrate on the homogeneous case. So when b of t is 0. Alright, so we're going to look at x prime equals ax. No t's in the matrix, and then no extra vector of functions on the end. I claim that the solutions of this homogeneous system of differential equations, x prime equals ax, form a vector space. To see this, well, so the solutions are vectors of functions. And vectors of functions clearly form a vector space, if we include the ones that are not solutions. So the vectors of all functions, or I should say all vectors of functions. Maybe all vectors of all functions, just to be extra sure. They clearly form a vector space. But I'm saying that this special collection of vectors of functions that are the solutions of H form a subspace of that. So we just need to show that it's closed under scalar multiplication and addition. So let's let x and y be solutions of H. So x prime equals ax and y prime equals ay. And let's consider all linear combinations of those. So we want to know, is c1x plus c2y also a solution of the system H? On the left-hand side, we have, if we look at just the derivatives, so the derivative of c1x plus c2y equals c1x prime plus c2y prime. On the right-hand side, we have, what if we plug in c1x plus c2y where there's an x here? So a times c1x plus c2y. That is c1ax plus c2ay. But ax is x prime and ay is y prime. So that equals c1x prime plus c2y prime, which is exactly what we had on the left-hand side. So yes, if x and y are solutions and c1 and c2 are real numbers, then c1x plus c2y is also a solution. So yes, these do form a vector space. And even though we're concentrating on homogeneous systems, let me just mention a fact. The solutions of a non-homogeneous system like this do not form a vector space. So this proof relied on the system being a homogeneous system. So the solutions to a homogeneous system, x prime equals ax, are typically an infinite vector space. I guess unless the solution space is the zero space containing just the zero vector. But if it's one-dimensional or two-dimensional, then we have infinitely many solutions, because we can, at the very least, multiply by infinitely many different real numbers. And sometimes we want to know which solution, if any, satisfies certain conditions. This is called an initial value problem. And often those conditions are what happens with the functions at time 0 and their derivatives at time 0, something like that. So for example, we could ask, does any of these solutions so we found two solutions to a differential equation before. One of them was e to the negative 3t negative 2e to the negative 3t. So since the solutions are closed under linear combinations, we could say, does any of the solutions some multiple of this plus some multiple of the other one, which was e to the 2t 1/2 e to the 2t, does any of those solutions satisfy x1 of 0 equals 1 and x2 of 0 equals 0? I guess I could write this in vector form with just one equal sign. Let's check. x1 of 0 equals 1 means that 1 is equal to, let's see, x1 is going to be c1 e to the negative 3 times 0, because we're plugging in t equals 0, plus c2 e to the 2 times 0. No, e to the 0 is just 1, so this is just saying that 1 equals c1 plus c2. And x2 of 0 being 0 means that 0 equals c1 times negative 2 e to the negative 3 times 0 plus c2 times 1/2 e to the 2 times 0. And again, e to the 0 is just 1, so this is saying negative 2c1 plus 1/2 c2 equals 0. Alright, so if we combine these two equations, gives c1 plus c2 equals 1, negative 2c1 plus half c2 equals 0. And let's add 2 times row 1 to row 2 to get rid of the negative 2c1 here. So we have c1 plus c2 equals 1, negative 2 plus 2 ones is 0, 1/2 plus 2 times 1 is 2 plus 1/2. It's 5/2. And 0 plus 2 ones is 2. So that means that c2 equals, multiply both sides by 2/5, and I guess we have 4/5. And then if c2 is 4/5 and the numbers add together to give us 1, I guess c1 has to be 1/5. So the solution we want is plug in 1/5 for C1 and plug in 4/5 for C2. So if we're given, say, a general system, a general solution with unknown constants in it, like a basis of a solution space, then initial conditions will help us identify one solution in that solution space that satisfies these conditions. The end.